Hi, in this video I'm going to be showing you how to use the visible light microscope and sample stage application for moving your sample around in the X-ray beam at the X-ray Microprobe station at GSECARS. Hi, I'm Matt Newville, one of the beamline scientists for the X-ray Microprobe station at GSECARS. In this video, we'll assume that you have already connected to Ferrari, the control computer, and know how to move the screens around and see the various control applications. Here again in the upper left we have the view of the sample from an in-hutch camera. So here we see a sample, and on that, going down to the microscope view, we see a 1 millimeter field of view. This is a 100 micron scale bar. We have a center point defined, and we can see how to manipulate the sample around with these controls. So we have several stages that can move the sample around, and several applications that can, or several controls that can change the visible image that we see from the sample. I'm going to go back up to this main view, and we're on this molybdenum foil, but I'm going to move off of that. So to do that, I'm going to use what we have called coarse stages. So we have vertical and horizontal stages here. I'm going to make about 1 millimeter steps and move the sample. If I click the up button, the sample will move up. And as I do that, you can see that both the microscope image is moving and the foil is moving out of the beam, or in the beam. And as I go up, it's gone out of focus. So we also have a focus control. This distance here is 52. You can think of that as the distance away from the microscope. So a bigger number will move the sample away. And if I do 500 micron steps, it gets closer to in focus. We have several controls for continuing to drive around. In fact, we'll try to get that in better focus. And one thing that you can do is, well, you can click the autofocus button, which for highly reflected samples seems to work pretty well. For transparent or semi-transparent samples like glasses, it can often fail, but it's not a bad thing to try, even if it fails occasionally. With this screen, there's a couple of things that you can see. Again, we have the controls for the sample stages themselves, with changing the step size. These are all in millimeters steps. You can change to much bigger steps, and then you can drive the sample right and left. I'll make smaller. Right and left. Move the sample to the left. Move the sample to the right. Move the sample to the right again. Move the sample up and to the right, and then focus the beam. We often leave this at 50 micron increments to focus the beam, and then there's an autofocus, as I said. You can also you can also use the image to move to a position to the center point, which is approximately where the beam is. Not perfectly, but close. So if I select this point here, just by clicking on the image and then click the move selected pixel to center, that will move that position close to the center of the image. That's a fine way to drive around once you get close, if you're looking for something in particular on your sample. In addition, any place you want to do some analysis, you can save a position. So I will save this position. I'll call it frame, simply by going up into here into the save position and typing any name you would like and hitting return. That does a couple of things. It saves it into this list so that I can drive away and then come back to this by saying frame go to. This pops up a window saying, do I really want to move to that position? It saves all of the coordinates for all of the positions, all of the motors we're using. The sample stage has both the coarse stages that we've moved so far, and it also has fine stages on top that are closest to the sample. And if I move those around, that also moves the sample left and right. In fact, you can get confused and move these fine stages when you move these fine stages around, when you really should have been moving the coarse stages. We like to use the coarse stages to move the samples around from one sample to another, and then the fine stages are only used for X-ray fluorescence mapping or to go to a position from the maps. So, but And that's mostly because these fine stages have much less travel range than the coarse stage. The fine stages are more precise and they're closer to the sample, but they have less lifting capability and less travel range. But if you find yourself stuck at a place and say, oh, but I want to remember this place, but it's far away from 0, 0, the center of travel for those stages, you can click on the 0 fine motors that will send these positions to 0, move the coarse stages to adjust, and still be looking at approximately the same place on the sample. The sample isn't particularly interesting. It's a piece of aluminum, but we can go to a more interesting sample. So I'll click on the granite, which is much further away. We'll watch that move as I click OK. In fact, I'll scroll up here and say, go to granite. This window will come up, and you can see that the sample stage is making a pretty big move. It's going past several samples. We'll come back to the phosphors that glow in the beam in a second. This is just to show you that we can move to this granite that we'll use later in this video series, and go to this position on the sample. Now that we're on this position, we can use other applications to look at the data coming off of that particular sample. But for now, we can just say, well, that's an interesting point. Let's move to there and maybe look at the fluorescence spectrum from there. You can also see that on this application, there are other controls for lamp intensity, that you can turn the light up or down. You can change the exposure rate or change the gain on the image. This camera is actually very good at very low light. So if you can turn the gain way up and turn the lamp down, intensity down. This lamp intensity is a number that goes from 0 to 5 as full on intensity, and you're free to change that all you want. With the lamp off, you don't see much image unless I turn the gain way up. And you can play with these all you want. There's nothing that will go wrong. That's obviously a noisier image, so I'll turn that gain back down. You can also see that as I'm doing this over real VNC to my home computer, that there's a little bit of a lag, and sometimes the image gets jumpy as it's a pretty high resolution image, 2000 by 2000 pixels in color, that is being sent over real VNC. Also, you may have noticed that there's this little box down below, and if I click on a point on the map in the image, it will show a zoomed in version of that image. That's just the image zoomed in, and here that box is 150 microns across, and I can change that to say 50 microns across to really zoom in and be able to see the pixel level. As I change the focus, that is more obvious. That more obviously goes out of focus. So if you're trying to focus well, that can be a good thing to look at if you're focusing by hand. And also, if you click on a point, or maybe this little triangle here, that shows up, and then move selected pixel to center will bring that to the center and center the image on approximately that same point, as well as we can do the resolution. We typically keep this at about 100 microns also, so that you can see 100 millimeter field of view here in the sample microscope. Again, it's fine to save positions or to go back to other positions. So here's go back to granite. That was the original point that I saved as granite. We'll come back to that. But you could say granite 1A, and that's a fine thing to save. And that will just show up. In addition, I should say you can also erase this position, or you can show it. To do show, this image will show up. That image is saved in your data set. In fact, for here, I will go to the folder for this data set. We're in 2021, and this is the folder demo. And if I go here, there's sample images and a sample stage.html file. If I click on that web page, this will show all of the positions that we've saved in order. So here's at the bottom, here's the last image I saved, and that's the image that's in your folder that goes with you home with you in your set, and also has all of the positions for that, so that we can return to it even if disaster happens and we've lost all of the positions. Finally, I will say that if you are at the beamline, or you're sending us samples that you have good optical or backscattered images of, and you know exactly where you want to analyze, we can use our offline microscope with these sample stages and save positions and then transfer the positions from our offline microscope. That works pretty well to within 100 microns or so, so within the field of view, so that we can pre-find many points to analyze in your sample, and then you can refine those instead of having to hunt around with this combination of only a 1 millimeter field of view and only this sort of 1 inch round field of view. If that's something you're interested in and you feel like you can send us samples ahead of time, let us know and we will be happy to work that out with you. Let me now go back to the phosphor and show you the beam on the phosphor, especially at 20 keV. So if I click on the cadmium tungstate phosphor that we have, we will see the beam glowing in the image. So here is that cadmium tungstate phosphor glowing in the beam. It's slightly out of focus. I'm not going to worry about that right now. But then on the microscope view, we see this, which is the beam glowing blue on the sample. So you can see the beam position isn't perfect. It's close to that circle, but not perfect. And that the beam here in this view looks much longer than it is tall. That's because the sample is sitting at 45 degrees to the incident beam, with the right side being closer than the left side. So the X-ray beam comes in at 45 degrees, hits the cadmium tungstate about in this position, and then penetrates deeply into the cadmium tungstate at 20 keV, and that optical light coming from that absorption deep into the sample gives this tail off to the right. But what that means is that as if I focus and defocus the beam, you can see that because the sample's at 45 degrees, the beam moves right and left. So our ability to know where the beam is, depends on how well you can focus the beam. And if I hit autofocus, this ought to do a decent job on this sample, but it's not always perfect on the phosphors because they're translucent. Actually, that looks like it's doing okay, but you can see that the beam was dancing around right and left. And if I move the focus by 50 microns, the sample position, or the beam position on the sample, will also move by 50 microns. It moves right and left, but not up and down. So as you're driving around, you can trust the height of the beam pretty well. But if you want to know exactly where you're analyzing, it's best to do an X-ray fluorescent map and trust the X-rays at what they tell you. Also, if you have done that, you want to not tweak and adjust the focal position, because that will move the X-ray beam right and left as well as in focus. So I think that's for now enough for the X-ray microscope and visible light images. We will talk about these more as we collect data. We'll circle back to all of the applications, but that's the microscope and driving your sample around. So I hope that's helpful for you using the X-ray Microprobe beamline. Thanks.